here's an overview of gases for our test this week. In the center, I placed gases with the kinetic molecular theory, since the kinetic molecular theory is meant to show how all gases are actually related to each other. You'll remember there are 5 postulates, basically that particles are moving randomly, collisions are elastic so that they don't lose any energy. We've got temperature that actually dictates how the motion is going to be. You've got your attractions that actually don't interact with each other, and that your particles of the different gas molecules is completely negligible since the size of the container is significantly larger. Across the top then are your 4 variables. Collisions are your pressure. The empty space of the container represents your volume. Temperature is going to be shown by motion. And n, which is our number of particles, is going to be just counting. You'll remember as we started the unit, we looked at both non-flexible containers and flexible containers. In a non-flexible container, the pressure inside the container that's created by the gases is completely independent of anything outside of the container. So if the particles are moving faster, you can increase the pressure. When we instead have flexible containers, your internal pressure will be dictated by the external pressure. So the container will change sizes in order to accommodate that possible change in pressure. We had 4 direct relationships that we took a look at, including pressure and moles, pressure and temperature, volume in moles, and volume and temperature. Regardless of which one you selected to plot on the y-axis, if you plotted the accommodating variable on the x-axis, you would get a straight line. That allowed us to make this proportion here, so that any of your variables could be set up as a proportion in order to do the calculation. Remember, however, that temperature must be in Kelvin and N must be in moles. We also took a look at the inverse relationship. That was our 3rd lab. And the inverse relationship said that if we plotted pressure and volume, we actually ended up with this curve. That's how we knew it was an inverse relationship. So instead of having a direct proportion, we have a multiplied proportion here. If you joined all of those different relationships together, we have the combined gas law. So remember, you can use the combined gas law for any of these, because every time you want to look at 2 variables only, the other 2 variables are going to be held constant. So you would just cancel them out. At the same time, if you wanted to look at 3 variables and one of them wasn't mentioned, for instance, you can assume that that one is also constant and cancel that one out. This relationship then allowed us to set up the ideal gas law so that we had an R value representing all the different gases that were possible, since they're all going to behave the exact same way. It's a little easier to use that equation as PV equals nRT, especially if you're doing stoichiometry, because every time you want to use 22.4 liters on your mole map, you can now instead insert PV equals nRT to do the calculation. Remember, the R value is going to be found on your yellow sheet, so match your R value to the units of your other 4 variables. We also discussed how we could set up a wet gas. So Dalton's law of partial pressures is actually based on that original relationship of pressure and moles. With Dalton's law of partial pressures, that then means that we have the total pressure being represented by just adding all the pressures together, and the total moles represented by adding all of the moles together of the various gases. So again, you can see a nice direct relationship, but now instead of it just being a gas at some point in time compared to itself, we're comparing one gas, that's A, to the total number of gases, that's total. You can also do this calculation for wet gases. So if you see that we've collected it over water, or it's termed a wet gas, those would be tips to also knowing that the total pressure is equal to the gas pressure, plus a little bit of that water that's gotten trapped in there because it's evaporating. That water pressure, remember, you can find on your yellow sheet as well. When you then take and do this sort of calculation, really all you're trying to do is subtract so that the gas pressure that you plug into PivNert will allow you to calculate for the moles of that particular gas. Last but not least are just a little tip on essay writing. And so if you remember, as we practice essays way at the beginning of the unit, I asked you to keep in mind what the independent variable was doing and how it was changed, so make sure that you state that. Describe how the particles are then being affected. So are they moving faster? Are they colliding more frequently? Are they trying to push against the sides of the container? And then when you're thinking about that container, remember that the flexible versus non-flexible container is going to really impact what will happen with those variables. Last but not least, in your essay, please also then tell me the result of your dependent variable. So did it go up or did it go down? Ladies and gents, I do hope that that helps a little bit as you're reviewing for your test this week.